Hi, welcome back. In this lecture, I want to go a little bit beyond the first introductory lectures, and I want to define what is quantum machine learning, and I want to discuss briefly also his historical development. So what is quantum machine learning, or QML? QML is really at the intersection of machine learning, classical machine learning, and the quantum computing. So it's looking at how to apply analog machine learning technique using a quantum computing. So the application of machine learning techniques using quantum computing is QML. What is the key idea? Well, quantum computers are involved at some stage of the model training or data generation. So it might be that not the whole workflow is actually executing on a quantum computing system, but just some stage of the algorithm itself. For instance, we can make a pass forward in the neural network, and we can use optimizer on the classical system. Right? So this will be hybrid. And we'll see that today most of the algorithms are somehow hybrid. Not the whole workflow is executed on the quantum computing itself. The scope of quantum machine learning is actually a broad field that range from quantum enhanced machine learning to fully quantum models. So when quantum machine learning was started? Well, it was starting around 2009, 2010, and that's the main reason is the development of a quite famous algorithm called HHL that allow to solve a linear system. So there is a first phase of a quantum machine learning that is based on the two basic technologies, HHL and the swap test. A second phase is focused more on the usage of feature maps and variational forms and the highly hybrid that roughly 2016 to today. So the first early quantum machine learning phase is based on two basic techniques. The first one is the HHL algorithm from the inventors of the algorithms, Haro, Hasidim, and Lloyd in 2009. What it does? Well, it solves a linear system. So given a linear system, the HHL algorithm allows us to encode it first, and then apply a quantum circuit to estimate what is the solution of the linear system. The second major algorithm is the swap test. The swap test is a method that allows us to compare different quantum states. So it can be used for measuring similarity between different data sets. Right? And you see here the quantum circuit for the swap test. So obviously, if you know how to solve a linear system, you can make a PCA, principal component analysis, or you can do a least square analysis. In the same way, if you have a classical machine learning technique such as k-means or clustering, then you need somehow the concepts of distance and can use the quantum swap test. So many of the first algorithms in machine learning have been focused on using these quantum primitives. The focus of this course, however, is to focus on the most modern machine learning approach based on feature maps, quantum kernels, and variational forms. So we are not going to discuss this technique that are more like a classical quantum computer, quantum machine learning. Instead, we're going to focus on this most modern technique based on quantum kernels and variational forms. So in the second phase of quantum machine learning, there is a shift in studying and investigating a quantum equivalent of classical kernel methods. So quantum kernel methods provide an alternative to classical kernel function that you probably heard before if you took a class on machine learning, by using quantum computers to map data into higher dimensional spaces. So we're going to encode classical data, apply a quantum feature map, and encode it in the quantum state. So you see here this process. So we have the data space in the classical part, and then we use some quantum circuit to map to some quantum space, feature space. And then we're going to use quantum circuits to compute inner products between the data points in the quantum feature space. We're going to devote a few lectures on this, so do not worry if you cannot grasp right now all the concepts. So the second main shift in the quantum machine learning is to look at so-called parameterized quantum circuits, or PQC. So these quantum circuits have parameters that can be optimized via classical machine learning algorithms. So the quantum circuit itself, executed in quantum computing, we are going to get a measurement of a certain observable, and we're going to use this measurement to calculate the loss function. After we calculate the loss function, we're going to use a classical optimizer, so not anymore a quantum computer, to calculate a new set of parameters that we can feed back in our quantum circuit. So this approach is much more flexible than HHL or a swap test based approach. It enables building quantum models that mimic classical machine learning structure very closely. The key characteristic is that these PQC use adjustable parameters to perform tasks like classification and regression, and the optimization itself is done on classical computing using classical optimization technique such as gradient descent. I want to finish up this lecture by describing you the famous classification of quantum machine learning approaches provided by Maria Schult and Petruccione in their book. So the classification is dividing data in classical data and quantum data and algorithm, classic algorithm and quantum algorithm. The first kind of approach is classical, so classical algorithm, classical data, where the algorithm itself is inspired by quantum techniques such as tensor networks. So this is not really our major interest. An interesting and the focus of this course in this part here, where we have some classical data and we apply some quantum algorithm. So we're going to focus very much on this. So we are having input that is from classical data, and we are going to use processing using a quantum computing system. Another interesting class of algorithm is this one, where we're using quantum algorithms on quantum data. Quantum data can be, for instance, from some quantum sensing device that provides us data in so-called superposition, or what we can also think, we have a quantum simulation, for instance, for quantum chemistry, where the output is given us in superposition of a quantum state. So that's also interesting. However, most of the examples of this course are in this category here. This is the last slide of this lecture, and talk to you soon.